There's a lot of ways to balance a redox reaction, and in this video I wanted to introduce you to one method, which is called the oxidation number method. For some of this, it's going to seem pretty common sense, but it will get a little bit more complicated in further videos when we take a look at more examples, but I really just wanted to start slow and introduce you to the idea. So this is the example that we're going to work through. So we have copper reacting with silver as an ion to produce solid copper or solid silver, and copper ions. Now, one thing you may think is like you could just go 1, 1, 1, 1. You have the same number of atoms on each side. You'd be totally balanced. But there's an important thing that we need to balance in all chemical reactions, not just redox reactions, that you never really think about until now. The charges in these are not balanced. And in any chemical reaction, not only do the number of atoms have to be balanced, but the total charge on both the reactant side and the product side have to be equal. And so that means that's one of the things we're going to have to deal with. But whenever we're working with the oxidation number method, and really with any redox reaction, our first step is to walk through it and find the oxidation number of each substance. Because one of the big things we need to do with redox reactions is find what was oxidized, what was reduced. So copper, pure element, oxidation number of 0. Silver is an ion, so its charge is its oxidation number. Copper, also an ion, so its charge is its oxidation number. And silver is a pure element, so its oxidation number is 0. From this point, what we need to do is take a look and see, okay, copper was oxidized. It lost 1 electron. The silver went from +1 to 0. The silver gained 1 electron, and so it was reduced. In order to balance this, what we're going to want to do is, first of all, take a look at our two substances that are actually changing. And so this may seem pretty common sense here because there are only 2 substances, but in some reactions there are many, many elements that you need to deal with. So we need to look at what is our substance. We want to figure out what is the initial oxidation number. What is the final oxidation number? So in the case of copper, its initial oxidation number was 0, whereas silver, +1. Final oxidation number for copper was +2, whereas the silver was 0. So then we need to look at the change in electrons. And just so you know, triangle means change, so change in electrons. Well, there was a loss of 2 and a gain of 1. We need these to be equal. So we need to essentially multiply this by something. So if you think about it, we can multiply 1 by 2 and 2 by 1, and that'll give us 2 in each case. We're going to ignore the positives and negatives, the gained and lost, because we just need them to actually exchange the same amount. That's a really important thing about redox reactions, is they exchange the same amount of electrons between each of the substances. You can't have electrons not accounted for. But what this also tells us is, using these numbers, it tells us our balancing coefficients. And so what we can do is we can say, okay, copper, well, that's going to have a coefficient of 1 because I multiplied it by a factor of 1. Whereas the silver is going to have a coefficient of 2 because I multiplied it by a factor of 2. And then you can see we not only have the same number of coppers and the same number of silvers, but I have a positive 2 charge, like 2 total positives on the left and 2 total positives on the right, meaning that I now have a totally balanced redox reaction. So this was a pretty simple example. I think now would be a great time to take a look at one that's a little bit more complex. So let's wipe this clean and start over. Okay, so you can see this is a much more complex equation than we've been dealing with up to any point so far. So big, so complex that I had to like lift the camera up just to fit it all in. So we have a lot of things happening, but we're just going to break it down the exact same way we have in every other example. We're going to start by looking at what are our oxidation numbers. So let's start with iron. Iron is easy, has an oxidation number of +2, and you know what, this one's easy too. It actually tells us what the oxidation number is with the charge. The same thing here, +2. This may be hard to see at that height, but that's a +3. H2O, that's also pretty easy. Anytime oxygen's in a compound, it's a -2, whereas hydrogen is a +1. And then the only tricky one here is the MnO4. So we have a -2 for the oxygen. There are 4 of them. That gives us a total of 8 negatives, and it needs to add up to be -1 because that's the charge. So that means manganese, the one manganese here has to be +7. Hopefully you can get to the point where you're not using the chart to do your calculations and you can just kind of figure it out in your head. But if you're not at that point yet, keep using the chart until you get there. So does anything actually change here? Well, manganese pretty obviously changes. It goes from a +7 to a +2. So if we're going to start building our chart and we want to take a look at our elements or substances, whatever you want to write here, the very first thing we're going to write is Mn because we know that its oxidation number has changed. What else has changed? Well, oxygen hasn't, hydrogen hasn't, but iron has changed. So we want to look at our initial, we want to look at our final, and then we want to look at our change in electrons. That's what we need to know here. Straighten that out there. Okay. So the manganese starts as a +7 and ends up as a +2, which means it gained 5 electrons. Whereas the iron started as a +2 and went to a +3, so it had to have lost 1 electron. So now what we need to look at is what are we going to multiply by? So we need to multiply the manganese, well, just by 1, and the iron by 5. And that's going to give us 5 electrons transferred in total between each one. This is the important part because this gives us our coefficients. So the manganese, we're going to put 1s in front of the manganese. The iron, well, it's going to get a 5 in front. And now you may think like, okay, we're good, but we're not good. And that's because the H's and the O's are not balanced. This method right now doesn't actually address those, but we can fill those in after. We know this has to have a coefficient of 1 because of what we calculated down here. Because of the amount of electrons changed, this coefficient cannot change from what it is there. It is basically fixed as this number. And same thing here, this one is fixed, same with here and here. They are stuck and locked in where they're at. So that means we're going to have 4 oxygens no matter what, which means I can balance my 4 oxygens over here, which then gives me 8 hydrogens, which I can balance out on this side by giving myself 8 hydrogens. And at this point, if you were to figure out, you have 1 Mn, 1 Mn, 4 Os, 4 Os, 5 irons, 5 irons, 8 H's, 8 H's. My total positive charges, I have 18 positive charges, 18 minus 1, so 17 positive charges on the left. 5 times +3 is 15, plus 2 is 17. 17 positive charges on the right. Charges are balanced, atoms are balanced, equation is balanced. So this is how we use the oxidation number method. We look at our initial, we look at our final by figuring out the oxidation numbers of the things that are actually changing, and then we multiply to make sure that the number of electrons being exchanged is equal between those two elements. So thanks for watching, and if you need more examples, please check out the other video.